So let me start. The title is the liquid film dryout and droplet transfers in annular two-phase flow. The contents are listed here. First, some brief introduction I show you. And the droplet transfer can be divided into two parts. One is the droplet deposition, and second, the droplet entrainment. And in the talk about the droplet deposition, first I will talk about the experiments, measurement methods, and some modeling. And after that, another trial is to understand the droplet motion by numerical simulation. So the two methods were used to understand droplet deposition. One is experiment, the other is numerical simulation. And for the droplet entrainment, I don't know exactly, but numerical simulation of droplet entrainment is very difficult. If you imagine, at least in the case of air-water two-phase flow, liquid film is much less than 1 millimeter. But you know, the channel is at least 1 meter long, 0.1 millimeter, and 1 meter long. Aspect ratio is very, very big. Therefore, it means that if you simulate such a liquid film, a numerical simulation, both type, volume of fluid type numerical simulation, how many computational cells are needed? I do not want to calculate it. So it's very different. And as for the entrainment, I only talk about experiments. And if we use a droplet deposition model and droplet entrainment, a prediction of the critical heat flux by film flow model is possible. And what kind of dryout prediction can be obtained, I will talk about this. And these are the main part of this talk. Deposition, entrainment, by using these correlations, critical heat flux by liquid film dryout is predicted. And as the additional topics, I will talk about the secondary entrainment. Details will be described later. And also, in the case of a boiling water reactor, if we have a spacer, we know it is known that critical heat flux increases. And the mechanism, and no one knows the detailed mechanism. However, many people believe that enhanced deposition by the obstacle is the main reason of the CHF enhancement by the spacer. Therefore, I also did some experiment about this. I will talk about this. And the final one is the conclusion. So, the introduction, overview of the liquid film dryout. And this is a schematic view of the boiling two-phase flow. Because the channel wall is equally heated, therefore the vapor quality increases gradually. Therefore the flow regime changes from bubbly flow, slug flow, and annular flow. And here the dryout occurs, and after that droplet flow becomes you observe a droplet flow, but the wall temperature is dramatically different, annular flow and droplet flow. And the important point in annular two-phase flow, liquid phase flows partly liquid film, and also remaining liquid phase are flowing as droplets. And if the heated wall is exposed to vapor phase, if the liquid film is depleted, and this is a transition to this part. This is a transition to the critical heat flux condition. And in order to calculate as shown here, if all the liquids flows as a liquid film, in this case, prediction of critical heat flux is very, very easy. And because all the liquid is, if all the liquid is flowing in the liquid film, dryout occurs when the equilibrium quality becomes unity. Therefore, this kind description of this equation is rather time-consuming. Therefore, I skip this. But if you calculate this equation, critical heat flux can easily be predicted. And however, in reality, even if the critical the quality is less than unity, dry out occurs here. And as you can see, liquid film is depleted here. However, there are still remaining many, many droplets. And in the case of a high pressure situation, it is possible here half of the liquid can flow as droplets. It's possible. So therefore, how many liquid is flowing in droplets and in liquid, it's very, very, very important. あれこれ動かねえか。Yeah, I can only show you the snapshot today. But this is the side view of the annular fluid vessel. And if this moves, you can see the disturbance wave. Sometimes the big wave propagates here. And this is, if you do a study in the field of annular fluid vessel, you have to know this name, Hewitt. And this was, I received this movie from Hewitt. And this is the movie of the annular two-phase flow. And the channel is like this. And the film is horizontal. But from the end of the tube channel, he observed, take to this movie. And this is the droplets. And this is really intermittent, not so steady state. Disturbance wave comes and big droplets. So it's very and if you see this movie, you may feel that modeling of annular two-phase flow is almost impossible. Therefore, I recommend you not to see this movie. But anyways, the difficulty of the complex phenomena included in the annular flow can be understood from this movie. And one method is to predict the critical heat flux. It's an empirical correlation. And many empirical correlations are available for the critical heat flux, like this. And usually, these correlations are based on the water data and the dimensional. One reason maybe is because I'm Japanese, therefore I recommend Kato's correlation. Kato is a very, very memorial professor in the University of Tokyo. And in his correlation, he accumulated many data for many critical heat flux data. Various fluids were used, and the correlation is this form. It's dimensionless form. And the critical heat flux was scaled by using the flow rate and the latent heat of vaporization. And he assumes that this is a function of 3 x, k, and subcooling number. And also, this is okay, I'm sorry, I made a mistake. And this functional form is not so complicated, but here is two parameters, x and k. And in the case of Kato, he assumes that the x and k are the functions of the three parameters. The one is the dimensionless channel length and the density ratio, and this is magic number. I don't know why this is, but anyway, I think after many trial and errors, Kato succeeded to find out this parameter. And if this parameter is used, critical heat flux data can be collapsed very well. And these types of correlation, the advantage is very easy to use. Just calculate these parameters, you can calculate the critical heat flux. And at least within the range of database, very accurate. And the drawbacks, it cannot be used outside of the database. And these data are usually the critical heat flux is measured in uniform heating. So therefore, if there is an ununiform heat distribution, it cannot be applied. And for the university professors, drawback, this is not directly related with physics. A professor is usually, if the correlation is developed, why? Next step, the research is not finished, so we can get salary. Yeah, that's it. Okay. The next, before talking about the droplet transfer, deposition, and entrainment, I would like to talk about the outline of the film flow analysis. Why do we want to develop a good correlation for the deposition and the entrainment? Main purpose is accurate prediction of the critical heat flux by liquid film dryout. And the flow rate of the liquid film, how can we predict this one? First, the liquid film flow rate decreases by the evaporation and droplet entrainment. Okay? And how the liquid film flow rate increases is due to the droplet deposition from the gas core to the liquid film. And if these physics are expressed in the form of differential equation, the change of the film flow rate in the axial direction can be expressed by using the deposition rate and the entrainment rate and vaporization rate. Okay. To solve, in order to solve this equation, several quantities are needed. In the calculation, film flow rate is calculated from the starting point of annular flow. And after that, some droplet deposited and some droplet are entrained, and the actual change of the film flow rate can be calculated. And in the film flow analysis, usually a critical heat flux is defined as the minimum heat flux at which the local film flow rate becomes 0, like this. Okay? The drawback of this method is it is not I would like to emphasize this point. Usually, young people believe that complicated model is better than the simple model. But it's not always true. If you compare the, for example, Kato model and the film flow model, in the experimental condition, there is a experimental database, many experimental data available. In that case, Kato model is more accurate. But in this kind of a complicated model, in specific condition, in my experience, it is not very accurate. But in this model, mechanism is included. Therefore, even if the condition is slightly different, but if the mechanism is similar, in that case, this model can be applicable. Therefore, the feature of the model is a bit different between the empirical correlation and this kind of mechanistic model. But this kind of drawback is present. The advantage is here, and this is more mechanistic, so it's interesting for me and applicable to non-uniform heating and applicable to even in the unsteady situation, mechanism is the same. So the prediction is still possible. So I think this is the most important point. Extrapolation to different situation is easier. Okay. So to calculate this equation accurately, the crucial issue is how many droplets are deposited is difficult. And how many droplets are entrained with a liquid film, it is also difficult. The crucial points are how can we have an accurate correlation for this part and this part. So I'd like to talk about this. Maybe this should be skipped. Of course, you may know there is two types of critical heat flux. One is liquid film dryout, and in the case of PWR, critical heat flux condition is induced by the departure from nuclear boiling. This is a bit different from the liquid film dryout. Therefore, and also I think that in Korea, main nuclear power plant is a pressurized water reactor. Therefore, maybe in your case, DNB is very important. But today, the topic is droplet transfer. So sorry, but I skipped this. If you have some comments on this, I would like to talk about this later. Okay, so I would like to move to the droplet deposition. And the experiments after that numerical simulation. I'd like to talk about the experiments first. And this is the measurement principle of the rate of droplet deposition. I'm sorry, I did a mistake. And this is the experimental facility I used. It's rather difficult to understand. And this part is the flow channel. And it was 5 millimeter in diameter. And the mixer is here. Here the liquid and the air is mixed here. And annular flow is established here. And at this point, only liquid film is extracted from the inside of the tube to the outside of the tube. And okay.
In my laboratory, we use that method too, like the film extraction method. In our laboratory, I maybe think that liquid film and air is extract from
Simultaneously, yes.
So that is that I believe the drumlet trajectory is impacted by that gas flow. So how to
the answer is shown here. And anyways, a principle is here. This is the extraction section. And the outside of the extraction section, this is some equipment. And the outside pressure is decreased gradually. If the pressure is decreased, more fluid is extracted from the inside of the tube to the outside. Okay? And here the horizontal axis is the air. It was extracted from the inside to outside. Okay? If the pressure is decreased, first the amount of air extracted is 0. The situation, the expected situation is like this. This is the extracted section. And the first liquid film is like this. And the first pressure here is decreased. Some liquid, only liquid is removed. And the pressure decrease, and the pressure reduction. Water is extracted. And however, if all the liquid is extracted, after that air comes from with the liquid film. At this time, in this figure, horizontal axis is the amount of air extracted with the liquid. And as you can see, air is extracted, and this is entry limit fraction means essentially the rate of liquid that is extracted. And as you can see, if the air is extracted more liquid is also extracted. Because this vertical axis is droplet flow rate means, therefore the reduction means more liquid was extracted as the liquid film. Okay? And as you can see, you may expect that if the more air is extracted, more liquid is also extracted. However, this figure indicates that here, air flow rate increases, but the extracted liquid flow rate is almost constant. Why? This is the problem. The description is a bit complicated, but liquid film is in reality not like this, because there is a disturbance wave. Therefore, the true image of the liquid film is like this. Therefore, if pressure reduction is not so much, this part is extracted, okay? And the pressure difference is increased, this part is increased. And from here, not only liquid but also air is extracted from the tube. And if this pressure difference increase come from here, all the liquid film is extracted from inside to outside, okay? But yeah, in this case, with the liquid, some gas also extracts outside. Fortunately, the flow rate of air is increased gradually, like this. If, in this case, droplet also extracted with the liquid film, in this case, this figure should like this. However, you know how fast is the liquid film. Typical velocity may be 0.5 meter per second, for example. And droplet, how fast? It is, for example, 30 meter per second. Inertia is very, very different between the liquid film and the droplet. Therefore, it can be expected, even if some liquid film and air is extracted from here, even if the air is extracted, but the density of air and density of droplet is very different. Therefore, it can be expected, even if air is extracted, but the droplet inertia is very big, therefore, it can go straight. As a result, we can get a plateau region here. Therefore, if you gradually increase the airflow rate extracted, and after that, the extracted liquid flow rate is not affected by the airflow so much. In this case, the measured result is reliable, I think. But this is rather, in this, if you are lucky enough, you can get this kind of figure. So in this case, it's okay. But here, for example, high pressure steam water experiments, in that case, in this case, air inertia and droplet inertia is very different because near low pressure gas, air and water. However, high pressure case, gas phase density increases. Therefore, the difference of inertia between the gas phase and liquid phase come close to. In that case, this one, good situation, this kind of figure is good. But here, bad case, you have this kind of rather no plateau region can be obtained. In that case, you should do some determination. You have to accept some error in the measurement. Okay. Yeah, but anyway, thank you very much. It is the most important point in this measurement. And let me return to the talk. And the double film extraction method was used at the inlet of the lead deposition section. First, all the liquid film is extracted here. Therefore, only droplets is available. Okay, no liquid film. And however, these droplets redeposited to the wall, and new liquid film is created. And this new liquid film is extracted here. Therefore, we can assume that the rate of droplet deposition in this section can be equal to the liquid film extracted here. This is a basic measurement principle. There is one more important assumption, but it takes time to talk, so I skip it, sorry. The problem is this experiment is time consuming. It's not but this is, at that time I was a very patient student, okay. This is a method I used, and another method, the double dry out. In the case of liquid steam case, here the liquid film is extracted. But another case is this part is heated, and from the amount of heat, we can calculate the droplet film flow rate. Therefore, dry out method is also available. And also, if the wall is transparent, tracer method is also used. In this case, no transparent wall is not needed. And yeah, anyways, another method is available.
Professor,
Okay.
I have a question. Is there any effect of film extraction length when
Deposition length,
extraction length?
extraction length. Where to where?
Effect of,
Maybe here to here.
to both.
待てよ。You mean extraction length mean
Both media length.
yeah?
Yes.
I don't care of that, not so much. And I think the effect of deposition, porous section length is not so much. Because in principle, liquid film is like this, and this is the porous section, okay? And in the porous section, liquid is removed. And this is a situation. Therefore, if the section is shorter like this, the physical image is this one changed to this one. So in principle, it is not very. Did you have some influence of the? No. So I think it's not so. Okay.
Near the error interface, the large granule can be removed. So large granule is
Large.
small, low, and granule is removed.
You mean droplet also removed here?
Yes, large granule velocity is relatively low,
Mm.
yes, reason.
Okay, but yeah, what is the size you expect?
I think error interface granule size is, for example, 1 millimeter.
1 millimeter.
Yeah.
But yeah, I think big droplet is okay because this is a flow channel, okay, and the droplet to go out from this section. In this case, the droplet should basically, if there is no extraction, droplet trajectory is almost straight, okay. And for this droplet to be extracted here, it should move with air. Okay? How this droplet move with air or not is a balance, competition of the inertia force and drag force.
Well, granule also even near the error interface.
Okay? Around here?
Yeah.
Yeah? So therefore, in this case, there is a chance to droplet to go out with air. But from my experiment, it is depending. Of course, it depends on the experimental condition. But at least in this experimental condition, it is not so much.
In our case, horizontal height,
Yeah. Yeah. In the experiment, how high is the gas phase velocity, superficial gas velocity?
Year
30? I think if the 30 is not so, the gas phase velocity is not very high. Okay. Therefore, in my case, the situation is annular, the vertical flow. In the case of vertical flow, to obtain annular two-phase flow, rather high gas velocity is needed. Okay? And if the gas velocity is, for example, 10 or 20 meters per second, in that case, flow regime is a churn flow or something like that. And some counter current, churn flow is available. But in the case of horizontal flow, even if the airflow is not so much, you can have a separated, rather annular, similar to annular flow. Therefore, situation is rather different. So maybe in your case, a horizontal situation like this. Therefore, maybe you have this kind of wavy interface, and some droplet. So I'm not very sure. This is droplet or liquid film. It's very difficult. And how fast this droplet? It is a problem. The assumption in the annual flow, this is liquid film, and I mentioned previously, usually liquid film is much slower. And the droplet is included in the gas core flow. The velocity is 20%, 20 meters per second, 30 miles. In some cases, in this experiment, the droplet velocity is higher than 100 meters per second. In that case, the velocity of liquid film and droplet is very different. So it means that inertia is very different. So we can assume that only liquid can be extracted, but droplet stay in the core. However, in your case, like this, and I guess velocity of this droplet, how fast the liquid film. Therefore, in your case, visualization is possible. You can visualize. No. So I don't know if it's possible or not, but I recommend you to compare how fast the liquid film and how fast is the droplet. If velocity of liquid film and droplets are almost the same, in that case, separation is very difficult. So, yeah, I cannot explain more detail, but yeah, in that case, very difficult. Okay. Maybe you are facing a very, very difficult situations, but please try your best. Sorry. Anyways, these are the measurement principle of the deposition rate. And by this method, we measure the deposition rate. And first, we investigate the parametric trend. And usually, how is the droplet deposition is expressed? This one. M sub d is the deposition rate of droplets, and it is unit is kilogram per square meter per second. Okay. And this one is similar to this. The big assumption is that deposition rate is proportional to the droplet concentration. Very simple assumption. Okay. If there is 10 droplets, 3 droplets are deposited. 10, 3. If 20, 6. 100, I forget how many. 30. 30. This is a very simple assumption. But measurement results does not agree with this simple assumption. But sorry. The concentration is sufficiently low. Kd is nearly proportional to the gas velocity. It's okay. If the gas velocity is high, turbulence is more significant, then maybe more droplets come to wall. So it's understandable. But high concentration, this is a very famous figure by McCoy and Hanratty. This is maybe, this part is most important. As you can see, some parameter is constant. This implies that the conclusion is this one. This proportionality factor is proportional to the gas velocity. So it's very simple situation. However, if the concentration is very high in this case, the vertical axis is essentially the mass transfer coefficient, Kd in this equation. And the horizontal axis is the droplet concentration. How many droplets here? And you can see, if there are many droplets deposition becomes more difficult. Therefore, the proportionality factor decreases like this. Okay. So if the concentration is high, proportionality factor decreases with an increase in the droplet concentration. So it means that 10 droplets, 3 are deposited. 20, only 4. 30, the calculation is too difficult for me. But measurement result is like this.
May I ask something?
Okay.
What is the criteria between low concentration and high concentration?
Experimentally, this one. Okay, and this is a Goban's fit. Goban's opinion that here the K is constant, but here the K is decreasing. So my opinion is a bit different, but Goban's opinion is the trend is different from. So maybe this is his standpoint. Rather, from the experimental data, K is rather constant here, but it starts to decrease from here. Therefore, from this data, but how do you explain this data? So there are difficulty. But from the experimental data, about 0.1 or 2 or 3 around here, there is a critical point. So, in many cases, in annular two-phase flow, at least the boiling water reactor, C is high. Such a dilute droplet flow is only available the aerosol problem or something like that. In annular two-phase flow, air and paper and water flowing very, very aggressively. Therefore, there are many droplets usually. The one point is I tried to do some numerical simulation to reproduce the droplet motion in turbulent pipe flow. And in the simulation, I used large eddy simulation because the droplets to accompany with turbulent flow. Therefore, it's easier if such a unsteady flow is reproduced in the simulation. A flow is this way, the droplet also come here. So large eddy simulation was selected. And the droplet in my simulation individually tracked as so the particle tracking method was used. And in this case, therefore, the force is exerted on the droplet, drag force and lift force. Gravity, it is almost negligible. But no, I'm sorry, this is a mistake. Gravity is very important. Why? Because such a drag force, particularly lift force, it's proportional to the velocity difference between a continuous phase and particle. Therefore, the gravity itself does not directly affect the droplet motion. However, the relative velocity is determined by gravity. Therefore, as a result, lift force is affected, and so deposition is also affected. So it is important. And also, this is very important in the simulation. Two-way interaction is. Therefore, the continuous gas phase affects the droplet, and the droplet also affects the continuous phase motion. It's very important because the droplet alters the turbulence. This is a big assumption, but in my simulation, if the droplet is moving this way, and if the droplet touches the wall, it is deposited. It's the assumption. The more detail is because my students are very familiar with this description. I'm not so much. So please do not ask too much details to me. But anyway, the Smagoriski model is constant. This one is used. This is reliable, I think. The drag coefficient Clift model is used. I'm good at this. The lift coefficient Safman model and some modification is done. And in this calculation, initial condition is also important, but the location is randomly distributed. And maybe it is not so bad, because Professor Hewitt also measures the droplet concentration distribution, and as a result, the droplet concentration distribution is not so reasonably uniform. And velocity, this is a problem, but in the simulation, in the actual direction, I assume that the relative velocity is initially 0. It may be more improvement is necessary, but anyway, I did this. The numerical result is shown here. dependence of the proportional factor on C is consistent. So therefore, in this figure, horizontal axis is droplet concentration, and the vertical axis is K, mass transfer coefficient. As you can see, if the concentration is low enough, it's not affected by the droplet concentration. However, at high concentration, deposition tended to decrease. This trend can be obtained. So this can be obtained. So in the experiment, it's very difficult. Why high C, K decrease? But in numerical simulation, we have all the phenomena in the simulation result. Therefore, we can investigate why. And at high concentration, turbulent velocity decreases and viscous sublayer thickness increases like this. This is the log law distribution. However, if the many droplets are included here, the velocity distribution becomes like this. Therefore, droplets affect the turbulent structure, and as a result, droplet deposition is also affected. And you can see these are the turbulent velocities, and this is, I guess, this is axial component, and these are the radial component or peripheral component. And you can see concentration is low, radial component is very high, but if many droplets are included in the core part, turbulence velocity is mitigated significantly. So it is very, very reasonable. Deposition rate is decreased. The reason is the forces exerted by the droplets change the turbulent flow field in gas phase drastically. This is one of the main causes of the reduction of K. And in this experiment, in this simulation, droplet collision is not taken into consideration. So therefore, it is another mechanism of the reduction of K, but it is not reproduced here. But basic concept is like this. This is a flow channel, and there is a turbulent eddy like this. And here, the droplet goes through this turbulent eddy, and this is very, very rough explanation, just an image. True physics is a bit different from this one, but the image is this eddy is divided to two parts. Yeah, we are friends, and hand by hand, but some guy goes through here, and it is divided to two groups. And in this case, if a big turbulent eddy is present, droplet come here, its trajectory is influenced, for example, like this. However, if this one is divided to two small eddies, in that case, this is affected like this. The next, this one is affected like this. In this case, first come from here to here. It's likely to deposit. In this case, this one randomly different direction. So as a result, trajectory becomes like to straight one. So this is the basic mechanism of the reduction of the deposition rate with the increase of the droplet concentration. And anyway, my correlation is come from the experimental data. And from the numerical simulation, it was shown that the droplet transfer coefficient is affected by the droplet concentration very much. Therefore, this is not my correlation, I think, in my opinion. This is just the Govan's data, using the Govan's data, and some modification was done, just I fit the data. And anyway, considering the effect of the droplet concentration, mass transfer coefficient is correlated like this.
I have a
Okay.
question. Why are you to not include the drop size in your equation model?
Too difficult question. It is not directly included here. And I guess here, the to derive the number, the scaling the K and C, and particularly here the surface tension coefficient is included here. Therefore, I guess this one considers, not directly, but indirectly, the droplet size effect is included here. Because this is an empirical correlation, and if the following topic is droplet entrainment, there is many physics. However, this is rather empirical one. I guess, Goban and Hewitt made many trials, and after that, if these two dimensionless numbers are selected, experimental data are collapsed like this. Therefore, I guess droplet size effect may be included here, but yeah, that's the only answer I can show you.
Professor, why is the error so deep?
But yeah, in my opinion, this error is not so big. Okay? Please check the more deposition correlation. In that case, one order difference is not surprising. Oh, just one order, it's okay. In the case of deposition. Yeah. Maybe mixing method, there are many uncertainties, and the deposition phenomena, just the droplet come from here to the wall. It's not so complicated process, I think, but yeah, physics is really complicated. So if you check another researcher's results, this scattering is more significant. In some cases, very beautiful collapse can be observed. But in that case, there is a trick. Experimental range is not so much. Many researchers do experiment, only air water, and only using his data, correlation is developed. In that case, in his paper, agreement with the data is perfect. However, just taking other data here, it's 10 order different, something like that. So in this, I would like to emphasize minus 50 to 100% in this complex phenomena. And I don't talk about it anymore, but situations like that. And next, droplet entrainment. First, in the case of droplet deposition, we can measure. But yeah, direct measurement of droplet entrainment is very difficult. And how do we measure the entrainment? Theoretically, it's rather difficult. Let me read this. If droplets are entrained into gas core flow, like this, some of them should be deposited. Okay? If there are 100 droplets, maybe 1 or 2 droplets deposited. Okay? If so the conclusion, there are droplets. Some deposition should occur. Okay? No method, in that case, no method is available for direct measurement of the entrainment rate. Okay? So we have to take indirect measurement. But yeah, there is only one method. If interface behavior can be visualized perfectly, in that case, you can directly measure the entrainment rate. So maybe some of them try it, but it may be, it's difficult. But anyway, in my case, we selected the indirect measurement and for the adiabatic annular flow. Here, droplets, and it has liquid film. Some droplets are entrained and some droplets deposited. So, for example, 2 droplets deposited and 1 droplet entrained. In this case, the liquid film flow rate increases. Okay. As you can see, deposition is more, film flow rate increases. And the entrainment is more, film flow rate decreases. And from the experiment, film flow rate becomes constant sufficiently downstream from the mixing section in adiabatic annular flow. Okay? These are the facts. Therefore, we can assume that entrainment and deposition are equal in the equilibrium situation with annular two-phase flow. This is a basic principle. Therefore, two indirect methods are available. One is first, deposition rate is measured in the equilibrium annular flow. And in the equilibrium situation, we can assume that entrainment and deposition are equal. Therefore, if you can measure the deposition rate, it's equal to the entrainment rate. Oh, it's okay. This is one method. And one more is measure the entrainment fraction in the equilibrium annular flow. Entrainment fraction, you may know, it's the definition of the entrainment fraction is the droplet flow rate divided by liquid flow rate. It's the sum of the film flow rate and droplet flow rate, okay? So, in order to measure the entrainment rate, there are two methods, measurement deposition or entrainment fraction. Two methods are available. And the next, the talk about the measurement method is finished. I'd like to move to the model development. And in the case of deposition, it was fully empirical. But in this case, some mechanistic concept was included. And why entrainment occurs? And the driving force, I assume that the shear force by the gas flow. Very, very high velocity gas flow is present here. Therefore, the shear force try to remove droplet from the liquid film. This is one assumption. And what is the resistance? And here, the liquid film are friends here, hand by hand. Therefore, even if there is some shear flow, they try to don't go to with the air. This is a surface tension. And the interfacial shear can be is proportional to the this one energy, kinetic energy of the gas phase flow. And the surface tension is of course the surface tension coefficient divided by the. This is trick. It should be the curvature of the interface. But the one assumption is. But yeah. Liquid film shape is like this. How can we evaluate the curvature here? But yeah, my assumption is if the film is thick film may be like this, thin film like this. Therefore, my assumption is curvature radius may be proportional to the film thickness. Thick film curvature is like this. So from this competition of the shear and the surface tension, therefore, as the dimensionless number which characterize the entrainment rate, this kind of a dimensional parameter can be deduced. This is the most important assumption I used when I developed my correlation. So I hoped measured data of the entrainment rate can be expressed as a function of this dimensionless number. And because this was successful, I talk about this today. The assumption is, anyway, the entrainment rate can be expressed as a function of this one. And if there are some more variables here, but from the experimental data, mass transfer coefficient for the droplet entrainment can be determined from the experimental data or not. This is the point. And some detail is talked about. In my case, the equilibrium entrainment fraction, by using this data, entrainment rate is correlated. First assumption, in the equilibrium state, entrainment rate and deposition rate are equal. Okay. Next, next assumption, this is widely accepted. Deposition rate is proportional to the droplet concentration. However, the K is also the function of C, so it's rather complicated, but it's okay. And the droplet concentration can be calculated. This. Is it okay? If the entry limit fraction is great, liquid droplet concentration is high, it's very easy. So please calculate by yourself after the seminar. It's not so difficult. This is the assumption, but not so bad. Liquid film thickness is very, very thin. And also, droplet velocity and gas velocity is almost equal. Okay? Do you have a doubt about this? Okay? No problem. Well, thank you very much. And also, it is assumed that ME, the entry element rate, is expressed by this functional form. So this most important one is this one, pi sub E. Pi sub E doubled, entry element is also doubled. This is a basic concept. And after that, this one is the surface shear force divided by the surface tension. Therefore, we should evaluate the frictional factor accurately. Density is okay, and the gas flow rate is the experimental condition, and how we can, and also the evaluation method of the film thickness is also important. And in my case, friction factor, interface friction factor is evaluated by Wallis condition. And one advice is that there are many interface friction factor correlations. And this is rather old one. And the previous recent researchers developed a more accurate one. But in my experience, in modeling this kind of very complicated phenomena, in many cases, simpler correlation is better. And next, how did I evaluate the liquid film thickness? And I assume that this liquid film is in the steady state. Therefore, wall shear force and interfacial shear force should equal. And if some correlation is inputted to this equation, we can evaluate how thick is the liquid film is by this equation. And here, E and entry fraction is also included. And this one is substituted here, and interface friction is substituted here. And if we use the relationship between this one and this one, and after that we can decide. Only unknown factor is Ke. If this can be fixed, it's okay. This is the result. From the previous equation, this relationship can be derived. And in this figure, R, what is R? I don't remember very well, but maybe this one. This part is the definition of R. And the vertical axis, E divided by one minus E. This is the left-hand side of this equation. And you can see I used 17 experimental databases, and the plots come from like this. So from this one, I could believe this relation present in the droplet entrainment process. And from the data, this exponent value and this proportional factor, the value was fixed like this. And I investigated the performance of my correlation using the entry fraction data. And there are many famous ones, Ishii and Mishima model. And this model is today no Ishii and no Mishima, okay? And maybe some of you are friends of never tell my talk to them. And their correlation was developed, and their correlation is very fine. But yeah, in the development process, they only use the air-water data. So therefore, it's very good for the air-water data. However, if this one is applied to steam water, big deviation is present. And the inverse, opposite one is the Goban and Hewitt model. And their main purpose is dry out. Therefore, in their case, steam, vapor water data was important, and they use a fairly good performance of the air water. But yeah, I'd like to talk about the Sugawara first. And Sugawara's purpose only was the drought prediction. Therefore, he decided only to use the steam water data. Therefore, good for steam water, but bad for air water, like that. And the Goban is reasonably good air water. But anyways, my correlation is good, but it's not very surprising because this is the more newest one. So the big advantage in comparison is the older one. And if the performance is not good in comparison with the available one, it's not worth to be published. Okay. So not surprising, but yeah, at least for this experimental database, comparison was reasonably good. So next, and now we have a reasonable correlation for the deposition and entrainment. And yeah, as someone said, deposition scattering is very, very significant. Is it okay? He said. So the next one is to check this can work in the prediction of the liquid film dry out. From the no, different investigators. So there was 17 sources were used. Okay. Measurement of what? At least air water and steam water method is different. There are many methods and many working fluids in various conditions. Data were accumulated. And I'd like to say, now we're just searching the publication in the personal computer. You can accumulate the experimental data. But yeah, this was published, I think, about 2000, about 15 or 20 years ago. At that time, accumulating this kind of experimental data was rather difficult. So therefore, I have to call to the United Kingdom. Please give me. And also, some of the data is not the Elsevier. Some of them are from the international journal of the heat and mass transfer, something like that. In that case, obtaining the paper is very easy. However, in all days, for the 1960 or 1970, Hewitt group published their data in a laboratory report. Therefore, getting that is rather difficult. So, but yeah, at that time I was young, so I could do that. Okay.
For your correlation, what summer hydraulic condition may be not properly. For example, high net flux, high pressure. Your correlation was summer hydraulic condition maybe not properly.
Maybe the answer is what is the experimental condition range of these experimental data sources? And some data come from the atmospheric pressure airflow, atmospheric steam water, and some one is from 70 bar steam water. So very wide range of experimental data are included here. So I think reasonably okay. But yeah, if other experimental data from another experimental conditions, but yeah, I hope still prediction is reasonably good. But yeah, main reason is at least the entrainment correlation is based on the concept shear force is the driving force of entrainment, and surface tension force is the resistance of the entrainment. If this assumption is reasonably okay, I hope prediction result is also okay. But please detect my correlation does not work very well. In that case, please let me know. And if you would like to know the detail of this one is published in the Heat and Mass Transfer journal. Therefore, please check it. So the next, I'd like to move to the prediction of the critical heat flux. And it's very easy. Not easy. Several more items are included. And at the beginning of this talk, I said if you have a good correlation with deposition and entrainment, dry out can be predicted easily. It's not true. This is the equation we should solve to predict the critical heat flux. But some more correlations are needed. First, this integration, where the integration starts, it starts from here. So therefore, to integrate this equation, first, in this equation, liquid film flow rate is calculated. But this is the integration procedure. Therefore, here, how much liquid flows as liquid film, it should be predicted. And also, usually the calculation starts from here, bottom of the annular flow region. And where the flow regime changed from slug flow to annular flow. This should be predicted. And in my case, first, when the flow regime go to annular flow. In this case, I use the Wallis correlation. And this is reasonably okay, I think. The difficult point is how many liquid is in the liquid film. And at this time, I assumed that the entrainment fraction at the transition is equal to the equilibrium situation. I don't know if this is okay or not. And but how can you measure how many liquid are droplets here? It's experimentally very difficult. And in the case of Goban, they assume that, I don't remember very well, 90% of the droplet, 90% of liquid flow as a droplet. This is Goban's, 90% is mistake of 95 or 85. I don't exactly remember the value, but he assumes that the entrainment fraction here is constant. But in my case, my assumption is this one. In my opinion, this is better. Okay. And next one, this is also a very important topic. I said dry out occurs when the film flow rate becomes 0. This is also not true. Okay. The image of the liquid film is like this. And when dry out occurs, maybe first the dry out occurs here, not here. Okay? But the film flow rate calculated by this equation is the some kind of averaged value. Okay? Time average or something like that. Because here, because the film flow rate is different here and here. Of course, the film flow rate should be greater here. But at the moment of the film dry out, maybe the situation is something like this. Dry out. Okay? Therefore, this G sub f, is the time averaged value, if we assume that. In that case, the time averaged value is not 0. Therefore, GF is 0 as a dry out is rather simplified assumption. So I'd like to repeat is to make integration of this equation to calculate film dry out, at least three more correlations are needed. One is when annular flow starts. And how many liquid film and how many liquid droplets as the starting point of annular flow. And when dryout occurs, these correlations are prepared, and the deposition and entrainment are used, and the integration is possible, and we can calculate the dryout. The next one, some more. The deposition rate, and basically I use the Govan's and my correlation based on the Govan's data. But there was some expression data was available. Therefore, Sugawa's correlation was also combined. And as for the entrainment rate, my model was developed by using the entrainment rate data based on the adiabatic annular flow data. But in the case of boiling two-phase flow, there is a possibility. Usually, we want to believe that phase change occurs here. Do you understand? You know the difference of the boiling and evaporation? Water is here. Evaporation occurs here. Boiling, heated, boiling occurs here. In the case of annular flow, liquid film is very thin. Therefore, I guess evaporation is very, very significant. So we hope main phase change from liquid to vapor occurs as an interface. However, if the heat flux is very high, in that case, boiling within the liquid is possible. And recently, for example, the International Journal of Mass Phase or something like that, presence of the boiling within the liquid film is reported. So in the diabatic condition, vapor bubble is created here, and maybe vapor bubble passes through the interface. In that case, droplet entrainment may be possible. In this case, shear entrainment, for this, my correlation can be applied, and also boiling entrainment may occur. And also, in my case, Ueda, he is also the professor of the University of Tokyo. He developed the boiling entrainment, and I used this one. But this correlation is really questionable, because in developing this correlation, Ueda's experiment is like this. This is a heater, and freely holding liquid film is formed here, and heat is applied, and some droplets is splashed like this. Liquid film is like this, and the droplets, and there is no airflow. And therefore, situation is very different in the experiment and the annular two-phase flow. There are some questions, and my Swedish friend said, if this correlation is used he measured the film flow rate, and if this correlation is included, prediction is completely different from the experimental data. So I don't recommend you to use this one, he said. But anyway, yeah. Okay. And next, now, anyways, correlations are prepared. All the correlations are prepared here. So next step is the calculation. And the database to compare, I used RAS. I hope you get some surprise. Many data were used. Round tube, it's round tube uniform heating, is very normal. And also Freon data is used. And the round tube non-uniform, chop cosine or something like that was used. And also non-circular channel, a circular tube and rectangular channel, triangular and dumbbell, like this. I don't know why Piero did this kind of experiment, but anyway, he measured critical heat flux in this situation. And this is also used. And before doing the calculation, we have to remove the DNB data. Because each experimental data, this is dryout, this is DNB, such information, of course, not available. Therefore, we have to select the dryout data from the CHF data. Some method was used. And the result is like this. And the, if you use the cut and on, this is empirical correlation of the critical reflux, and the result is like this. And the Gobern's correlation, some scattering is present. In my case, a little bit better prediction of the critical derived heat flux was measured. The prediction scatter is approximately plus minus 30%, and a little bit better than the previous one. So I think many physics are included in the occurrence of the liquid film dryad, but the main physics may be reasonably reproduced by my model, I think. Okay. And this is the result for the water data, uniformly heated round tube. But if the situation is more complicated, for example, this kind of circumferentially only half part is heated, the agreement is not bad. And even in the case of actually non-uniform heating, in this case, cut-off correlation cannot be used. But in my correlation, reasonably good comparison was obtained. And even it's a dumbbell shape. And you can see some kind of, in this case, some kind of deviation is observed. Maybe, for example, in this case, I guess, this is how thin is the flow channel. And in this case, I don't remember this parameter very well, but in this case, it means that aspect ratio is very large. In this case, I guess that in this shape, because of the surface tension force, the liquid film may accumulate to the corner of the channel. But in my model, a liquid film is uniform in the channel wall. So this is the main reason of the discrepancy. Therefore, I guess if how much liquid is accumulated as the corner part, such a model is further included, more good comparison is obtained. So maybe today I was go to the Dr. Yun's experimental lab, and this kind of a rectangular shaped channel was shown. That maybe, and also in that case, channel gap is 2 or 3 millimeters. Therefore, this kind of a phenomena may be important. I don't know the detail. Okay.
Why are you draw the line plus minus 30% error?
To show the how accurate the prediction is.
Or the graph have a 30% error line.
Yeah.
So,
Maybe I don't know the reason either. But maybe within me, plus minus 30% is okay. I maybe. Sorry. And so the main part of my talk is finished. And do I have Jajun? Jajun, are you sleeping? Little bit more is okay. How much time can I spend? Because if 5 more minutes, okay, hurry. Just the introduction of the additional topic. One, the secondary entrainment. Maybe this doesn't work. The phenomena is like this. Okay? This kind of a movie. And it is not so interesting for you, but it's interesting for me very much. And the surprise is this one. And the droplets impacts the liquid film. And in the development of the deposition modeling, we assume that droplet impacts the film, it should be absorbed in the liquid film. Okay? However, with this knowledge, it's okay. It's okay, very different from the situation in the deposition. But in this case, the droplet comes from here. Okay? Yeah, because this is a very, very important one, so it takes time. Too bad. This is like this. So as you can see, which is greater, impacting drop and splashed droplets? And I don't show you anymore. But yeah, at least it is not, the splashed droplets amount is not negligible. Don't move. Is it moving? Maybe Jajin say me to stop now. Yeah, it's freezing. The problem is there is a secondary entrainment or not. So I did the experiment, and at that time, almost all the experiments, there are many experiments with droplet and liquid film impacts. But yeah, almost all the experiments is a normal impact. But in my case, at least in the case of annular flow, impact is very, very oblique. Therefore, I studied the oblique impact experimentally. But yeah, please imagine this experiment is very, very difficult. How do you impact the droplet obliquely to the liquid film? But yeah, there is some trick. This is the surprise. Please forget the animation. And I measured first this one. This one is normal result of normal impact. And if the impact velocity is greater, more liquid is splashed. Okay. And the next one, this one is data for the oblique impact. And when the impact angle is 15 or 20, like this, slightly oblique. In this case, the splashed droplets is like this. And this means EM equals unity, this line. This line is impact droplet and the splashed droplet amount are the same. Okay? So if the plot is over this line, it means that if the droplet impacts the liquid film, not deposition, it means entrainment. This is 15. Next, next one is 45 to 55. Okay, more nearly unity. And next, and you can see the increase is 100 times. Therefore, in the case of oblique impact, many droplets may be splashed. But yeah, this is the influence of the impact angle. If the impact angle increases, more deposition, droplets are splashed. But if the impact angle is very, very great, in that case, the splash is stopped. Therefore, in the case of annular flow, like this. Therefore, I hope secondary entrainment is not so much. Okay. And another one is the obstruct effect. And this is the deposition and the entrainment drought occurs. And if there is some obstacle is present, how much impact on, how much influence on the deposition. And we made this kind of experiment facility. And this is a test section. And obstacle is placed here. In this case, dry out method was used to measure deposition. And the liquid film is dry out here. Therefore, here only droplets. And the new liquid film is created here. It is once more dried out here. And from the heat input here, a deposition rate can be measured. And also some structure is placed here, and the deposition is increased or decreased. It was measured. And the obstacle shape was rather simple. It's a cylinder. Not cylinder, the tube. Tube was used. And the result is here. First, critical heat flux was measured. Flow rate is increased. Critical heat increased like this. And this is anyways a result of the critical heat flux measurement. It's not very important today. And next, this one is important, deposition rate measurement. And as you can see, with an increase in the liquid flow rate, deposition, droplet concentration. This mass transfer coefficient. This is important. Concentration to deposition coefficient is plotted against the droplet concentration. And as I said previously, with an increase in the droplet concentration, a droplet coefficient decreases like this. And if the obstacle is placed here, as you, I'm sorry. I skipped this one. This one. As you can see, if there is no obstacle, the deposition rate is like this. Okay, with an increase in the concentration, deposition rate increases. However, if the mass transfer coefficient is constant, MD should proportional to CF, so the plot distribute should like this. However, with an increase in the droplet concentration, mass transfer coefficient decreases. Therefore, the trend is like this. And this one is obstacle is placed. As you can see, the deposition rate is, for example, if the concentration is 3, from about 0.3 to the increase to nearly unity. Therefore, 2 times or 3 times the increase was measured. And in this figure, the droplet mass transfer coefficient plotted against the droplet concentration. And these two dimensionless factors is no obstacle case, this correlation. And if there is an obstacle, this kind of correlation. Therefore, these scaling parameters seems appropriate even in this case. Maybe today I do not have enough time to describe detail of this figure, but it's very simple. In this model, assumption is too simple. Droplet comes here, and if the droplets impact to this area of the obstacle, it's splashed. May have some radial component of velocity, and this one all deposited to the wall. Okay, if the top view is like this, and blockage ratio is 20%, 20% of droplets are deposited to the wall. Very simple assumption. And it seems that this assumption is too simple. However, it predicts the experimental data like this. Not so bad. Therefore, some modification is done to this deposition rate increase in the presence of the obstacle, maybe predicted well, I hope. The concluding remarks, film flow analysis is very good, but to do that, as many correlations are needed. And the development of the correlation for each physics is very important. And in developing the correlation, if there is some physics is underlying, I think better prediction results is obtained. And also, we investigated the additional effect, secondary entrainment, and also the obstacle effect. That's it. And there's some more information is available in this publication, so please see if you are interested in. That's it. Maybe too long. Thank you very much.